All right, folks, I just wanted to come in and give you a little example of using T procedures with matched pairs data. So we'll jump in here and I'll kind of explain as I go. For their second semester project in AP Statistics, Libby and Catherine decided to investigate which line was faster in the supermarket, the express lane or the regular lane. So to collect their data, they randomly selected 15 times. Obviously very important, randomly selected. 15 times during a week, went to the same store and bought the same item. However, one of them used the express lane and the other used the regular lane. So they went to the same store and bought the same item. To decide which lane each of them would use, they flipped a coin. So now that makes it a randomized experiment. If it was heads, Libby used the express lane and Catherine used the regular lane. If it was tails, Libby used the regular lane and Catherine used the express lane. They entered their randomly assigned lanes at the same time and recorded the time it took in seconds for them to complete the transaction. So a couple of things I wanted to note. This is a randomized experiment. It was very important that they did the randomized part because they're not the same person. So it could be the case that one of them is just more congenial and one of them's like me and doesn't want to talk to anybody. And so that person would always get checked out faster because they're not making small talk. So it's important that we randomize who goes to which lane and we don't just send one of them always to the express lane and the other. Like Libby always goes express and Catherine always goes to the regular lane, because then our results would be confounded with their personality. All right, so what I want to do is construct a confidence interval for the true mean difference in wait times, and we're going to do it in the direction of regular minus express. So this is a case where it seems like we have two sets of data, but they're really just masquerading as two sets, and it's a single set of data because each piece of data is matched in a pair with another piece. So, for example, these two, the girls went to the store at the same time and they bought the same item. So those two particular pieces of data are paired together. We're not just comparing one distribution to another randomly. Each piece of data is paired. And so what we want to do is construct a third column, and that's going to be our actual column of data. And we want that column to be the regular minus the express time. And so when data is paired like this, it's called matched pairs. And again, it's just two sets of data, or one set of data rather, masquerading as two sets. So you have to do a little work to first get the set of data that you're going to work with. So, for example, we're actually subtracting in that direction. So we're going to do the right minus the left column. So if I did 342 minus 337, I would end up with 5 being the difference for that pair. I've preloaded my calculator here with all the data. And so all I'm going to do is use lists. I put express in list 1, I put regular in list 2. So now I'm going to say list 3 is going to be list 2, which is regular, minus list 1, which is express. And now I've populated my list 3 with the difference, regular minus express, in each pair of data, right? And that's the list I actually want to create my confidence interval from. And so now we're just going to go through and set up our state plan to conclude. Okay, so here we go. All right, so state. We're going to construct oh no, I forgot what percent. Let's do 95%. So, construct a 95% confidence interval for the true mean difference in checkout times, and I'm going to indicate the direction as regular minus express. Okay, so we're ready for our plan. And we'll start with random. I'll just say this is a randomly designed experiment. We'll go 10%. Now here, the population that we're talking about would be the population of grocery store visits for the girls, and there is no population there. So all we need to state is that the trips were independent, because that's really what the 10% rule is checking for, is independence between cases. And then large counts. So this is the first time we've had a situation where our sample size is less than 30. They only went 15 times, so it's not satisfied. But T procedures are something called robust, and that means they will still give you good inference as long as the sample itself isn't skewed. So with that in mind, what we need to do in the case that our large counts condition isn't satisfied for a mean is graph the data and sketch a graph and then make a statement that there's no extreme skew. And since we already have the data in the calculator, we can probably do this relatively quickly. So all we want to do is graph the individual, or sorry, rather the one that we're using, which is list 3. So I'm just going to go to my stat plot, turn plot 1 on. I'm going to make it a box plot. Whoops. Because box plots make it easy for you to see if there's any skew. And I'm just going to tell it I want it to come from list 3, which is the list we're using our data from, right? That's the actual difference in each pair of checkout times. And then I'm just going to do a zoom. No, I have to quit first, sorry. Then I'm going to do a zoom stat. So zoom stat is the 9th option. Oh, whoops, I forgot to check y equals, and I have another graph in there. So let me clear that out. All right, now, zoom stat, good. Even if there's a mild skew, all we're gonna do is sketch this and label the 5-number summary. So while you're looking at this, I'm just gonna be sketching this box plot. All right, so my minimum is -94. My Q1 is -17. My median is 30. My Q3 is 95. And my max is 246. All right, so let me bring you back to our slides here. And I'll just label that as reg minus express, and that's in seconds. All right, and then I just have to make a statement. Sorry, just trying to clean it up a little bit here. My statement's just going to be no extreme skew or outliers safe to proceed with T procedures. And I know it's a little bit tedious, but they want to see this. They're going to be looking for that when they're scoring your AP exam. So if when you're doing inference for a mean, the large counts isn't satisfied, graph your data set, graph your sample, and make the statement that there's no extreme skew or outliers and it's safe to proceed with T procedures. So, all right, so let's go to do. And for do, we're going to go full calculator here. So we just need to name this, and this is going to be a one sample T interval for a mean, so for mu. And we'll go back to our calculator, and here's something that's really nice. So let's go to the main screen. We're going to go stat tests. Remember that if it's for a mean, it won't say mean, it just won't say prop. So what I'm looking for is a T interval. Here it is. And so in this case, we don't have the statistics, we haven't calculated that, but we do have the raw data. So you can just tell it this is coming from raw data, and you just need to give it the correct list. Remember, our raw data is in list 3, that's where we put the difference. Frequency, you'll just leave at 1 always. Confidence level, whatever you want it to be. And then we'll go ahead and calculate it. And you just want to make sure you write all of this down. So real quick, I'm going to write it down while you're looking at it. All right, so our sample mean is 42.67 seconds. Our sample standard deviation is 84.02 seconds. And we end up with an interval from negative 3.862 to 89.195. I'll bring you guys back to our slides here. And all right, just so you remember, a good thing to list is the degrees of freedom, which is your sample size minus 1. So that would have been 14 for us. All right, and then we'll conclude. So in our conclusion, we're just going to say we are 95% confident that the true mean difference in checkout times, and then here I'll note that that's in the direction regular minus express, falls on the interval from negative 3.862 seconds to 89.195 seconds. So here we might want to say, okay, so do we have evidence that express is faster than regular? And the answer would be no, because if we had evidence that express was faster than regular, since we did regular minus express, all the values in our interval should be positive, right? But in this case, we have negative and positive values, and we actually have 0 in our interval. So it's just as likely that they take the same amount of time as it is that one is faster than the other. All right, that's it. Just wanted to get you that quick example.